This is a review of the sewage sludge problem from your midterm exam. Here's the problem statement. You may want to pause the recording now and reread the statement. The key concept to get in this problem in order to solve it is there's actually two different states of the sludge that we need to evaluate. The first is the raw sludge as it comes out of the sewage treatment plant. And we've been given the total tons that are coming out per day, and the water content and the specific gravity of the solids of the raw sewage. The second state is of the sewage after, the sludge after it's been dried. And at this we've been given information that has a water content 50% with a saturation level of 40%. We're also given that the treatment plant sells this sludge for 23 cents per ton. So the problem we really want to know, the answer we really want to get is what's the total weight of dried sludge that is produced each year? From that we could calculate the amount of money that we could earn each year. In order to do this, we need two different three-phase diagrams, one for each state. We need one for the raw sludge, and we need a second one for the dried sludge. That's a critical concept to understand. And you can't mix up the data from the sludge in its raw state from the data for the sludge in its dried state. So let's draw our first three-phase diagram of the sludge in its raw state. So here's my three-phase diagram. I'm going to measure just the weight in tons. Now I'm only going to do half the three-phase diagram because I don't need to know anything about volume here. The only thing this thing asks about is weight, and we aren't going to need to calculate volumes. So I'm going to calculate things in tons. We were given that the total weight per day, I'm going to do this on a per day basis and then multiply out to years at the end. So we were told that the total sludge produced per day was 200 tons. So we know the total weight. And we also know that the water content of that sludge is at 140%. So we can calculate the weight of the solids as the total weight divided by 1 plus the water content. So for our problem, that would be 200 over 1 plus 1.4. Again, notice I'm using a decimal form of the water content for this calculation. That's going to turn out to be 83 tons, so I can write that in my three-phase diagram. Now it's pretty simple to calculate the weight of the water. That's just the difference between the total weight and the weight of the solids, and that's 117 pounds. I don't actually need that number, but at this stage you might not have remembered that you didn't need it in the problem and calculated that anyway. So now let's look at the dried sludge three-phase diagram. So now here's my three-phase diagram for the sludge, the raw sludge. And the first question we ask ourselves is, so what's changed between the time that it came out as raw sludge and the time it was dried? Well, the solid material didn't change. When it dries, the water changes, but the solid doesn't. But the water, the quantity of water is going to decrease during drying. So I'm not going to have 117 tons of water, and I'm not going to have 200 tons of total dried sludge. But the 83 is going to remain the same. So let me erase those numbers, and let's draw a new three-phase diagram with a smaller amount of water. So we need to compute that amount of water now. Well, we know that the weight of the water is equal to the weight of the solids times the water content. We're given that the dried sludge has a water content of 50%, so all I need to do is multiply the 83 tons of solids times 0.5, and that's going to give me the weight of the water, which is 41.5 tons. I'm going to write that in my three-phase diagram. Now the total weight is simply equal to the sum of the weight of the solids and the weight of the water. Add that up and I get 124.5 tons, so we're going to call that 125 tons. So each day I'm producing 125 tons of dried sludge. Notice that's less than the 200 tons of raw sludge that comes out of the plant, because a bunch of water has been removed. So now all I got to do is calculate the total dollars per year. That's pretty simple. It's 125 tons per day times 365 days per year times 20 cents per ton, and I do that number, put that in my calculator, and I'm going to come out with $11,900 per year. And that's the answer to the problem. So let's quickly summarize some key concepts. So this is really just a straightforward weight volume problem. The key here is that you need to draw the three-phase diagrams to understand what's going on. If you don't draw the three-phase diagrams, it's very hard to understand what's going on. And the other key concept is that when soils change water content, the weight of the solids does not change. And this is a very important concept to get with soils. There's lots of reasons that the water would come or go from soils, and whenever the water flows in or flows out, a lot of things can change. The total volume can change, the total weight can change, the amount of water can change, the void ratio can change, but the one thing that never changes in that case is the amount of solid materials. I hope this helped.